Let's just quickly run down to the syllabus. What we've done already with respect to the syllabus is from 3.1 to 3.3 that we've covered already, right?
Yes.
3.4, what we've looked at is the difference between linearly and circularly polarized light, right?
Yes.
We've come across the concept of circular birefringence as well as circular dichroism, whereby circular birefringence only refers to the
Oh,
difference in the refractive index of left and right circularly polarized light in a chiral medium. Okay, both of them put together are nothing but chiroptical properties. So they'll be exhibited only if the medium is chiral. Okay, so circular birefringence basically talks about the differences in refractive indices of the left and the right circularly polarized light in a chiral medium. Whereas circular dichroism talks about differential absorption between the left and the right circularly polarized light. Once again, this is exhibited only when the medium is chiral.
chiral.
So what we have to now today do is look at CD and ORD curves. We have to look at what exactly is the meaning of cotton effect, how can it be applied, and there are a few empirical rules that have been included in the syllabi. One of them is the octant rule, and a subset of the octant rule is the axial alpha haloketone rule. So the axial alpha haloketone rule is not a new rule by itself. It's just that, I mean, it's the limiting case of a octant rule. Like whenever there is an halogen atom at the alpha position of a cyclohexanone, then it reduces the octant rule to something much simpler. So in that way, axial alpha haloketone rule is a simplification of the octant rule. Okay. We'll quickly recapitulate all that we discussed with respect to linearly and circularly polarized light, right? Now, this was the representation of an electromagnetic radiation, which has vibrations along the electrical field vector component as well as the magnetic field vector component, right? And as a property of electromagnetic radiation, the vibrations in the electrical field and the magnetic field component are supposed to be mutually perpendicular to one another. So this represents such a kind of a plane polarized electromagnetic radiation, which has electrical field component along one of the axes and the magnetic field component in a mutually perpendicular axis. Now, what is very significant to note here is that both the electrical field and the magnetic field components are in phase over here, indicating that they are reaching a maxima as well as a minima simultaneously. Right? And there is no lag between the maxima and minima for the electrical field component and the magnetic field component, right? What if there was a lag between the electrical and the magnetic field component, which is represented over here? Say, for example, if we look at the two sinusoidal waves reaching the maxima and the minima, which is somewhere over here, and they are not doing so at the same time. If you see, one of them is reaching a maxima first, and then after a slight lag, the other one is reaching a maxima. So the green and the red sinusoidal waves are not in phase. They are slightly out of phase. How can you put them slightly out of phase? When you try and push the electrical field component a little ahead or the electrical field component a little behind that of the phase, then you're going to get such kind of a disparity or two components of the electromagnetic radiation not exactly being in phase, right? The resultant then is no longer a plane polarized light. The resultant is then going to trace a circle. And this type of polarization of light is called as a circularly polarized light. And we've been discussing about it even in our last video, whereby the main concepts were underlaid based on whether you have a left circularly polarized light or a right circularly polarized light interacting with matter which is chiral, right? Few things about the circularly polarized light which one needs to understand is circularly polarized light by itself, an intrinsic property is chiral, and the right and the left circularly polarized lights are mirror images of one another and they are non-superimposable. That means that there is some chirality in the circularly polarized light itself. Because there is chirality in circularly polarized light, they are going to interact differentially with a chiral environment or a chiral medium. whereby one of them is going to be made to pass through faster through the medium. One of them can go through slower. One of them may be absorbed to a larger extent. One of them may be absorbed to a smaller extent. This is what is the origin of chiroptical properties when electromagnetic radiations pass through a chiral environment, right? Okay, this figure or this GIF is representing the two components of a plane polarized light. If we imagine this central line moving up and down, the point moving up and down as representative of a plane polarized light, I can think of two components of this plane polarized light, one of them being represented by the green circularly polarized light, which is the LCPL. It's going in the left or the anti-clockwise direction. And you have a red circularly polarized light, which is moving in the clockwise direction. I call that as the right circularly polarized light, right? Now, what is very interesting to notice, the RCPL and LCPL, when they combine, they give you a PPL, right? A plane polarized light is the resultant of combination of a right circularly polarized light with a left circularly polarized.
Left circularly polarized.
Perfect. So
yes,
the corollary of this can be that a plane polarized light can by itself be thought of constituted with two different circularly polarized light. So I could think of a plane polarized light being constituted of a RCPL component and a matching LCPL component, which is making a PPL or a plane polarized light, right? So the interaction of these RCPLs and the LCPLs, which form constituents or components of a plane polarized light, will result in some characteristic chiroptical property, right? And the last figure demonstrates that. In this, you are starting out with a plane polarized light over here. Can you see that over here?
Yes.
Right. Now, this plane polarized light enters into this cuboidal medium, which is chiral. Now, because of chirality, one of the circularly polarized light will move faster through the chiral medium as compared to the other, right?
Yes.
So if the left circularly polarized light is moving faster through the chiral medium as compared to the right circularly polarized light, you'll see a deflection in the plane polarized light by an angle that will make the molecule in the chiral environment as levorotatory. We give that designation because it has rotated the plane of plane polarized light to the left.
Left.
Right? Now, this property of a chiral medium not to show the same refractive index for RCPL and LCPL is called as circular birefringence, right? That's the phenomena or the principle, you could say, right? Likewise, you have another principle that's shown by electromagnetic radiations in a chiral medium, and that is called as circular dichroism. So shortly, some time back, I have shared this chapter with you, and this chapter happens to be from Jagmohan. The last chapter of Jagmohan is on optical rotatory dispersion and circular dichroism. And in that, you've been given some figures. Now, you remember drawing such kind of figures on the board previously.
Yes.
That's why we said that the right and the left circularly polarized light will start out from origin at time 0, and then they'll trace out a slight angle from the mean position once the time of t1 elapses, and they'll keep moving forward. And when you take a vector addition of these two vectors, which is done by a parallelogram method, you would see that the line that represents the vector addition would trace out points along this mean position. That means it's going to represent the plane polarized light, right? If, however, the rate with which RCPL and LCPL that move through a medium is not the same, that means the medium itself is circularly birefringent, then you're going to see some difference in the angle, or there is going to be an angle that is going to be made by the resultant of the two vectors, which can either be tilting towards the right of the mean position or it can be tilting towards the left of the mean position, indicating that the substance itself is either dextrorotatory or levorotatory. Another thing that also happens for a certain chiral medium and electromagnetic radiation passing through it is, rather than getting a plane polarized light at an angle, we get an elliptically polarized light, right? And this elliptical polarization takes place due to differential absorption. You see, there is a differential absorption between this arrow, which has been made smaller, and this arrow, which is made larger in size,
Yes.
right? And the differences in these sizes of the arrows just represent the different rate of absorption of LCPL against RCPL. If LCPL is absorbed to a larger extent as compared to RCPL, for notational purposes, I could denote it with a smaller arrow indicating that more of it is being absorbed, whereas the RCPL is being represented by a larger arrow indicating that more of it is being transmitted. That means less of it is being absorbed. So there is a differential
So,
absorption. Yeah.
the intensity is high or low depending on the concentration of a particular um, compound. Like if the levorotatory compound is less, then that particular arrow intensity will be less. Is
Now
it like that?
you are considering a case whereby you have a mixture of levorotatory and dextrorotatory compounds, right?
Okay.
What if
So
I
in this
start
there
with,
is
non-racemic वाला ना?
yeah, go ahead.
Non-racemic condition ना,
Yeah.
जहाँ पर
So
concentration आएगा तो.
what if I start with an enantiopure system?
okay.
Okay.
So okay.
If I
So
start with an
इसमें ऐसा आएगा.
enantiopure system, what is going to happen? I'm going to have only one enantiomer in my medium, right?
Yes.
हाँ.
Now this
Yeah.
enantiomer is also going to show differential absorption of LCPL and RCPL.
Okay.
That's because the medium itself is circularly birefringent.
Yes.
And
Yeah.
it also exhibits circular dichroism.
Dichroism.
Right? Why circular dichroism? Because circular dichroism is also a chiroptical property. If it is a chiroptical property in a chiral medium, the rate with which
It
the
will happen.
LCPL is absorbed and RCPL is absorbed by a chiral medium is going to be different.
Okay.
Right? One of them is going to be absorbed to a larger extent. The other one is going to be absorbed to a lesser extent. Of course,
Okay.
what Kosha you are trying to say will also be true if at all we are talking about a non-racemic mixture, but not an enantiopure system. So naturally, if I have enantiopure lactic acid, for example, right? And if enantiopure lactic acid should register an optical activity of plus 25, when it is 100% its plus form, right? Now, what if I take 75% of dextrorotatory lactic acid and I mix it with 25% of levorotatory? What is going to happen? Will the optical activity remain as it is or will it drop?
Drop, because
drop,
it has
right?
become 50% EE.
Exactly. So there your concept is going to come in, whereby you're talking about the presence of the number of molecules which can either exhibit LCPL or RCPL to be absorbed greater or lesser. What we are trying to establish over here is, if there is a chiral environment, then the LCPL and the RCPL will not be absorbed to the same extent. And this phenomena, this chiroptical phenomena is called as circular dichroism.
Okay.
The circularly polarized light are not absorbed to the same extent in a chiral environment.
So even for the circular birefringence, what we were saying was for an enantiopure thing only, na, that will rotate either to the left or right.
Yeah, but if at all you have, I mean, here we are not talking about external compensation. You're still talking about external compensation.
Okay.
I'm not talking about external compensation. I'm trying to reason out what is the origin of optical activity. Why is it that a chiral molecule should turn the plane of plane polarized light to either right or to the left?
Or left.
Right?
Understood.
Now, if at all we wanted to talk about origin of color, why does KMNO4 look pink in color? Then I can start reasoning out and putting some theories in which I can say that KMNO4 absorbs in the complementary color region in the visible spectrum, and therefore it will transmit a certain other type of color. Right?
Yes.
So that's how I can reason out that there is something called as a lambda max for KMNO4.
Okay.
Likewise, if I had to reason out, why is it that a chiral molecule shows rotation of plane polarized light either to the right or to the left, you can use the basic principle of circular birefringence. What is circular birefringence? A circularly polarized light is not traveling at the same rate through a chiral environment. That is called as circular birefringence. And because the right circularly polarized light may travel faster as compared to the left circularly polarized light. The resultant will make a plane polarized light which will be at an angle, like you saw in the previous example,
Yes.
right?
Yes.
So in this example, if the left circularly polarized light is moving faster than the right circularly polarized light, because the medium is chiral, right? It's a chiroptical property, only to be exhibited if the medium is chiral. If the medium is not chiral, both the right and the left circularly polarized light would travel through with the same velocity.
Yes.
In that case, you would say that the medium is not circularly birefringent, right? So circular birefringence is what? The refractive index of RCPL and LCPL not being the same in a chiral environment.
Yes.
Right? And refractive index by itself is nothing but C upon V, where C represents the velocity of light and V represents velocity of light in that medium. So velocity of light in vacuum, which has a constant value, 3 into 10 to the power 8 meters per second, right?
Yes.
And V is the velocity of light in that medium in which you are trying to probe the chiroptical property. Is that okay? So here we are trying to ask a deeper question as to why there should be a change in the optical activity, or what results in this optical activity criteria for a molecule when it is chiral. Why is it that the plane polarized light should either deviate to the right or to the left? And the reason why what we are attributing that to is a phenomena called circular birefringence, right? The rate with which RCPL and LCPL are moving in the chiral environment is not the same. Right? Not only that, there is one more chiroptical property. What is the second chiroptical property? Circular dichroism. What is circular dichroism? The relative absorption of RCPL and the LCPL in a chiral environment is not the same. If RCPL is absorbed to a lesser extent, there could be a possibility that LCPL is absorbed to a larger extent by the chiral medium. The medium is chiral, it is going to exhibit both circular birefringence as well as circular dichroism. Right? But in the previous video, we dealt with them individually. We were trying to reason out why should there be circular birefringence. So if you remember, we came out with a curve like this, right? Whereby we said that the final angle representing the line or the plane with which the resultant plane polarized light is coming out should trace out an angle to that of what is incidental, right? And this angle can then be called as optical activity of the compound, right? And what results in optical activity? The principle behind optical activity is circular birefringence. The rate with which RCPL and LCPL have moved through the chiral environment is not the same, right? That's one part of it. Second part, we also looked at circular dichroism. What is circular dichroism? You can have the RCPL and LCPL being absorbed to different extents when it moves into a chiral medium or a chiral environment. Okay, so such a phenomena whereby the right and the left circularly polarized light are not absorbed to the same extent when they move into a chiral environment is called as circular dichroism. Right? And you can represent this on paper by the sizes of arrows, indicating a smaller sized arrow represents more amount of that circularly polarized light having been absorbed. More it is absorbed, less is transmitted. Right? So when you take this LCPL that is shorter as compared to RCPL, indicating that your chiral medium has absorbed the left circularly polarized light to a larger extent as compared to the right circularly polarized light. And then when you start moving them in that 360-degree fashion along the circle, you would see that the resultant now traces out a shape called as an ellipse.
Elliptic.
Right? So what comes out is an elliptically polarized light. You incident a plane polarized light into a chiral environment. What comes out is an elliptically polarized light. Now the light is no longer plane polarized, it's actually elliptically polarized. What this tells you is, in this particular figure, where you see a plane polarized light moving into the chiral environment and a plane polarized light coming out, is not exactly a very, is not the true picture what happens. but it's a good approximation. Why is it a good approximation? Now, say for example, if this was an ellipse, okay, let's just consider that what you see over here is an ellipse with the major axis being 100 units and the minor axis being just 0.1 units. So it's just 0.1 units in this axis, right? But it is 100 units in this axis. Can you picture that in your head?
Yes.
The minor axis is very, very small and the major axis is quite large.
Large.
Okay. So I could say that if the ellipse was like this, in this case, this is the minor axis and this one is my major axis,
Major.
right? Now, what if my major axis was quite huge? Okay, and the minor axis was very,
सर
very small.
बंद हो रहा है, थैंक यू करके बता रहा कुछ.
हाँ मेरे में भी आएगा ऑप्शन.
क्या हो गया?
मेरे में आया, it has been.
We are closer to 40 minutes.
अच्छा, ठीक है, no problem. Once again, we'll start it out. Okay.
Okay.
So try and imagine that if at all I make the minor axis really small, it almost looks like a line. आप देख रहे हो?
Yes.
It looks like a line
Yes.
itself.
Yes sir.
That means because the degree of ellipticity is so small, you can approximate the elliptically polarized light which is coming out to be a plane polarized light.
Plane polarized.
It's an approximation, right? It will look like a plane polarized light only from far because the degree of ellipticity is very, very, very small. But if you go into the technicalities, technically it's not a plane polarized light coming out. It's actually an elliptically polarized light, right? And why is it elliptically polarized light when it comes out? It's because of another phenomena, another chiroptical property, which is circular dichroism, right? So due to circular birefringence, you have this particular
angle.
facing an angle, right? It's not coming out at the same angle as that of what is incident.
Incident.
And due to circular dichroism, it's coming out as an elliptically polarized light and not a plane polarized light. Is that okay?
Yes.
Okay. Moving back here. So you have elliptically polarized light coming out and the elliptically polarized light will come out at an angle. Now what is important to note is this formula over here. Can you see alpha is equal to? Can you see this formula? Right? It's also there on the PDF that has been uploaded to you on page number 475. Okay, the formula says alpha is equal to pi upon lambda multiplied by eta r minus eta L. Okay, let's try and understand this formula. This formula is trying to tell you the effect of circular birefringence on the plane polarized light. The plane polarized light will no longer come at the same, in the same plane as it was incident. It is going to come out at an angle. And this angle is given by this angle alpha, say for example. If this angle is alpha, what does this alpha depend on? Alpha depends on 1 over lambda, which is very, very important. Lambda is in the denominator. That means it's inversely related to wavelength of light that is being incident on the molecule. Bear that out in mind because our optical rotatory dispersion is just a plot of alpha versus lambda. Eventually, when we'll talk about ORD, we'll be talking about curves whereby alpha is plotted against lambda. Lambda is on the x-axis and alpha is there on the y-axis. Right? So pi over lambda, why is pi there?
Circumference का वो 2 pi r है ना.
Okay, if you go back a little to your mathematics, you had measure of angle
Degree
in
of
terms of radians as well as in degrees, right?
Yes, yes.
There's something called as radians and there is something called as degrees. So if you want to convert radians into degrees, then you'll have to apply the pi. Yeah, that's right.
Yeah, 180 or pi.
Right. So that's the origin of pi over here. Pi is not 3.14. Pi is 180. It's the conversion factor for converting radians into
radians into degree.
degrees.
Degree.
That's the reason pi is there, right? Now we have 1 upon lambda. Lambda is the wavelength of light that is being incident on the
Yes.
chiral medium. Then you have a difference between the refractive index of RCPL and LCPL. Is that okay?
Right, polarized light.
They've given you all of this also on page number 476, where lambda is the vacuum wavelength of light employed. Eta R and eta L are refractive indices of the medium with respect to the right and left circularly polarized lights. Then eta being the refractive index can be defined as C upon V, where C is the velocity of light in vacuum.
Light in vacuum.
And V is with the velocity of light in that particular medium.
Medium.
Right? Now, when
Yes.
the medium is dextrorotatory, alpha should be positive, right? That's how you define
Yes.
dextrorotatory substance, which has a positive
Yes.
degree of rotation of
Rotation.
polarized light, right?
Yes.
So when this alpha is positive, when will alpha be positive? When eta
When
R
it's is less than eta L.
when eta R is
Less.
greater, no? Eta R is greater than eta L.
Huh.
Only then will
Okay.
alpha be positive, right?
Yes,
Otherwise,
yes,
alpha
yes,
will
yes.
become negative. Are you following that? So for alpha to be positive, what is the criteria? The refractive index of right circularly polarized light should be greater than the refractive index of left circularly
Left.
polarized light. In such a scenario, you will get a dextrorotatory substance. If the right circularly polarized lights eta is greater than left circularly polarized lights eta, can you tell me whose velocity is larger? Is the VR greater or is VL greater?
VL.
VL is greater. Do you see that? Because V and
Yes.
eta are inversely related.
Inversely
They're not
related.
directly proportional. Are you following that? Likewise, for a levorotatory substance, alpha has to be negative. For alpha to be negative, this eta R minus eta L has to be negative, right? Because wavelength of light cannot be negative, pi cannot be negative. So the only factor that can be negative is eta R minus eta L.
R minus eta L.
This can be negative if eta L is greater than eta R. That is, the refractive index of left circularly polarized light is greater than the refractive index for right circularly polarized.
Right circular.
Okay. Moving down. Then you have circular dichroism. Circular dichroism is given as delta epsilon. Right? Which is nothing but epsilon L minus epsilon R.
Should not be equal to.
And in a chiral medium, the difference between the left and right circularly polarized light's absorption of electromagnetic radiation is not the same. And therefore, the difference will not be zero. When will the difference be zero? When the left and the right absorb to the same extent, then the difference is going to be zero. It's going to get cancelled out.
Yes.
And that will be possible if the medium is
achiral medium.
Achiral. If on the other hand, the medium is chiral, then you will have some residual ellipticity. This is called as ellipticity. Delta epsilon. Okay, and this delta epsilon, eventually they try to convert this in the form of radiance. So when you take it in the form of radiance, you get tan psi is equal to minor axis upon the major axis. So you're converting the difference in absorption into ellipticity, which is given by theta. I'll come back to it. One second. As of now, we have one property already established, which is alpha, right?
Yes.
There is another property, which is theta, and theta is given as molar ellipticity, and ellipticity is measured in degrees, right? Or it's a measure of an angle. By what factor is it elliptical? does the light become elliptically polarized, right? The measure
Okay.
of that is given by theta. Okay. Now, initially, when you're considering the differential absorption between RCPL and LCPL, what you are measuring is basically delta epsilon or delta epsilon.
Okay.
Where does this epsilon come from? It comes from your Beer-Lambert's law. A is equal to epsilon CL, where epsilon is called as molar absorptivity.
Absorptivity.
Right?
Yes.
Now, molar absorptivity does not have units of angle. Molar absorptivity has units of absorbance upon C multiplied by L. What if you wanted to convert the difference in absorptivity into ellipticity?
Okay.
That is the measure by which the light becomes elliptically polarized.
Okay.
Isn't it a function of difference in absorption? Right? More there is a difference in absorption, more elliptical the light would be. So there is a relationship between difference in the rate of absorption of LCPL and RCPL with the ellipticity of the light coming out. Okay. So what they've tried to do here is they've tried to convert the difference in absorption, that is delta epsilon, into a factor called ellipticity that can be measured. And that ellipticity, that degree of ellipticity is nothing but a measure of minor axis upon the major axis. Okay, that's given by tan of psi. Then they convert psi by taking tan inverse, and you get psi upon c into 1800 upon pi. Once again, the origin of pi is once again to convert radians into degrees.
So then why 1800? Shouldn't it be 180?
Should have been 180. That's a very good question. The reason why it is 1800 is because all your polarimetric measurements are done in 1 decimeter length. Okay, let me take you back to A is equal to epsilon CL. What is the value of L that you take for A is equal to epsilon?
1 cm.
You always take it as 1 centimeter, right? Why do you take it as 1 centimeter?
Because that is the fixed length, like in the instrument. Fixed.
So if you measure the diameter of a cuvette, the diameter of the cuvette will always be 1 centimeter.
Be 1 centimeter.
You're fixing the path length to be 1 centimeter in case of UV visible spectrophotometry. Right?
Yes.
Likewise, if you measure the distance of one polarimeter tube, a polarimeter tube universally across is 1 decimeter. 1 decimeter is nothing but 1/10 of a meter. 1/10 of a meter is 10 centimeter.
Yes.
Right? So 10 centimeters.
Yes.
So once again, when you apply 10 centimeters over there, then it becomes 180 multiplied by 10. So you get 1800.
Okay.
Yes.
You get that? Okay.
Yes.
See, we are not going into the detailed mathematics of how the difference in absorption has got converted into ellipticity. What we are just trying to understand here from this mathematics is we are trying to find a relationship between the difference in absorption of LCPL and RCPL, which is a function of the degree of ellipticity. More the difference, more the ellipticity. So qualitatively, at least we can establish that relationship. Right? So it's clear qualitatively that the difference between the extent of absorption of LCPL and RCPL would reflect on the ellipticity of the light. Right?
Yes.
Can you follow that? And how
Yes.
you can mathematically express the difference between the molar absorptivities and the ellipticity is given over here. Tan of psi giving you minor axis over major axis. This gets translated into psi over C because you are trying to remove the concentration dependence. Right?
Yes.
You want molar ellipticity. If you want molar ellipticity, you should remove the concentration dependence. How do you remove the concentration dependence? By dividing by concentration. So that's how the divided by concentration has come, right?
Okay.
This 180 is because you're converting it into degrees from the radian.
Yes.
Pi has come because you want it in radians first, and then you're converting it into degrees. And the factor of 10 has come because the path length in any polarimeter experiment happens to be 10 centimeter or 1 decimeter. Is that okay? Then they further went on to involve molecular weight of the substance so as to convert the ellipticity into specific ellipticity, and from specific
Okay.
ellipticity into molar ellipticity.
Okay.
Right? So that's how they've done some mathematical treatment over here so as to express this chiroptical property with theta. Why is this important? It's important because whenever you're plotting a CD curve will, let me show you a representative CD curve. That's a CD curve, right?
Okay.
A CD curve plots theta against wavelength. So the same theta which you've
Calculated.
Yeah, which you've got the mathematical treatment of over here, that theta is plotted on the y-axis
Max.
in case of a CD curve. And you get a curve like this, which represents delta epsilon. Can you see that over here?
Yes.
Delta epsilon means definitely it has to do with circular dichroism, CD.
Yes.
And the plot that you see over here is called as an ORD curve, optical rotatory dispersion. That's based on phi. Do you see the phi over here?
Yes.
Now, phi is something that is an extension of this alpha.
Okay.
Okay, I'll just. Okay. Okay, in this, do you have alpha? Can you see what is written here?
Huh.
Okay, the first equation which says alpha is equal to pi upon lambda multiplied by eta r minus eta l was also there in Jagmohan, isn't it?
Yeah.
But then the eventual conversions of alpha into specific rotation and then into molar rotation is not given in Jagmohan. Do you see that the treatment is very similar in case of ellipticity as well? We converted ellipticity into specific ellipticity and from specific ellipticity into molar ellipticity.
Molar ellipticity.
Right? Likewise, optical activity can be converted into specific molar activity as well as, specific optical activity and molar rotation, basically.
Molar rotation.
And do you see what is the symbol given for molar rotation?
Phi.
It's phi, right? Now going back to our plot here, you have delta epsilon, where delta epsilon is representing circular dichroism, and you have phi being plotted against lambda, which is nothing but optical rotatory dispersion.
Yes.
Right? Now, is this making sense? Why I was telling you that optical rotatory dispersion is based on circular birefringence, whereas circular dichroism is based on circular dichroism itself. Right? If you remember, if you go back to the last video lecture that we had, we were talking about the principle behind an instrumental technique. And we were listing out that if absorbance happens to be the principle on which UV visible photometry is based on, likewise, circular birefringence happens to be the principle on which ORD is based on.
ORD work, yeah.
Right? And likewise, circular dichroism is the principle behind a circular dichroism instrument. Right? There, the principle and the instrumental technique are exactly the same. Here, in this case, the instrumental technique is optical rotatory dispersion, because you are making a plot of lambda, plot of phi against lambda, basically. And the principle behind this is basically circular birefringence. Is that okay? Okay, so there we are. A plot of phi versus lambda is nothing but an optical rotatory dispersion. Okay. Now going back to the formula of alpha, where was lambda in this equation? It is in the denominator. If it is in the denominator, what is the relationship between alpha and lambda?
Inverse.
It's inversely related, right? So that means lower the lambda, higher will be the alpha. You agree?
Yes. Yes.
That is the reason commercial polarimeters are not often that sensitive. They are not sensitive because commercial polarimeters use the sodium vapor lamp as the source. And they are using sodium vapor lamp as the source, then the sodium D line is what is getting incident on the molecule. And the D line of sodium has its wavelength around 520, 530,
26.
right? So in
Yes.
that particular region, you have lambda. Now, since the lambda is quite large, the value of alpha is going to be very, very small at
Very
that
small.
lambda. What if I
Yes.
go on reducing the lambda? I go on decreasing the lambda from sodium D line to shorter and shorter wavelengths, then I'm going to see the magnitude of alpha becoming larger and larger for a compound, which is chiral. And a plot of the change in phi, which is the molar rotation, with a decrease in lambda is nothing but optical rotatory dispersion, right? So do you see this particular thing moving up,
Yes.
increasing in the positive axis, and one of them increasing in the negative axis, right? Now this is one of the applications of plane ORD curves. These are called as plane ORD curves, right? Now,
Yes.
when will you call a ORD curve as a plane ORD curve? When there is no anomaly like you see over here. Is this an anomaly?
Yes.
Why do you think this is an anomaly?
Because it's crossing the.
As long as you look at a mathematical expression which looks like this, alpha is equal to something upon lambda. What should
From
happen as
minus.
you go on decreasing lambda? What should happen to alpha?
Alpha will keep increasing.
It should continue to increase. So there should be an exponential
Yes.
increase, right?
Yes.
Should just go on continuing to increase. But does that happen?
Yes.
No, there
No.
comes a
Then there's a
threshold
decrease.
at which it crosses over and goes beyond the axis. So such type of area is called as a cotton effect area.
Oh, okay.
This area is called as cotton effect, right? All this area, what you see over here, is called as a plane ORD. Why is it called a plane ORD? Because it meets the requirement of this expression, whereby alpha is related inversely to lambda.
Lambda.
So long as this relationship is maintained, you are at the plane ORD curve stage. But there will come a stage for all molecules whereby the plane ORD curves will exhibit some cotton effect. And the cotton effect can either be a positive cotton effect, it can be a negative cotton effect, or it can exhibit multiple cotton effects, right? We'll come to why exactly cotton effects do arise. Why is it that you get something anomalous close to a certain value of lambda, right? But as of now, let's try and understand applications of these plane ORD curves, right? So long as you've not reached the wavelength at which there will be an anomaly, you are in the region of a plane ORD curve, right? Now, sorry, any difficulty?
This anomaly will be observed for everything in a particular region, or only some kind of molecules exhibit the anomaly?
Okay, let me just get ahead of myself. There will be a characteristic wavelength of absorption for all organic compounds. You agree?
Yeah. Yes.
Yeah. Will all organic compounds absorb above, say, 220 nanometers?
Yes.
All of them will absorb?
No.
Sir.
What is the requirement
No.
of an organic compound for absorbing light? What should it have?
Chromophore or
Exactly.
like.
So it should have a chromophore, right?
Yes.
So if I talk about aliphatic hydrocarbon, it's not going to have absorbance till 220. It's going to have its lambda max in the vacuum ultraviolet region.
Yes.
Right? But what if I put a carbonyl group, I put aromatic rings, I put such
then it will 220 and
have
above.
its lambda maximum somewhere between 220 to 300, 350 nanometers, right?
Yes.
And whenever you approach the lambda maximum of an organic compound, you will see an anomaly in the ORD curve.
Oh, okay.
So did you understand what is the correlation between cotton effect and the ORD curve basically, and the structure of the molecule? When do you see a cotton effect? when you start approaching the lambda maximum of an organic compound. Okay, at its lambda maximum, you're going to see a typical, kind of a phenomena called as a Cotton effect, which is an anomaly to the normal ORD curve. Okay, so that I didn't want to bring it up so fast, but because there was a question, I had to answer that. If you once again look at this figure, which is B, can you see that the CD curve has a maxima over here at this wavelength? Can you see that?
Yes. Yes.
That means this is the wavelength at which the compound absorbs to the maximum extent. Can I call this as the lambda max of the compound?
Yes.
I can call it the lambda max of the compound, right? And at the lambda max, you're seeing the value of molar rotation dropping to 0. You see that?
Yes. Yes.
And then it's crossing over and going to the other side.
Yeah.
So now does that make sense? That whenever you approach the lambda maximum of the organic compound, you'll start seeing some anomaly in the normal ORD curve. And it will start exhibiting something called as a Cotton effect.
Okay.
That's why your CD and ORD curves are always overlaid on one another. So you never get only a CD curve or only an ORD curve. You always get both. Provided the lambda maximum of the organic compound lies somewhere above 220.
Okay.
You'll not see a Cotton effect at all for a molecule that does not have any chromophore. Okay. So what if I have a hydrocarbon with a chiral center somewhere? That's possible, right? I could have, say, butane, okay? Or say pentane. Pentane
2-butanol.
Even butanol has an OH that can act as chromophoric. What if I have a quaternary carbon atom kind of a chiral center, which has a pentane kind of a framework, but at carbon atom number 2, there is a ethyl and a propyl or something like that.
Okay.
Okay. So I have a chiral center, right? But there is no chromophore. If there is no chromophore, then it's not going to have absorbance above 220. So it's not going to exhibit Cotton effect at all. It's only going to show a normal ORD curve or a plain ORD curve.
Okay. Good.